So, what is Kafka? At high level, Kafka is a log, and the easiest way to think about it is a shared notebook with three rules. 1. Programs only ever add new lines at the end. 2. Reading a line does not remove it. And 3. Every reader keeps its own position in that notebook. And those three rules explain almost everything people find confusing about Kafka: replay, consumer groups, lag, and why ordering works the way it does. So hold on to them. When I say log, I do not mean the application logs, right? The file where we print our errors and our info messages. That is a completely different thing. Think about your bank passbook instead, or your account statement. Every transaction goes in as a new line, one below the other, in the order it happened. And we cannot go back and change last month's entry. It is just sitting there. Kafka is that same idea, but shared between systems. And rule 2 is the one that surprises people. So let us be careful with it. If you have worked with a normal work queue before, this is where Kafka is different. In a queue, when a worker picks up a job, the broker hides it from everybody else. And once the worker confirms it is done, the broker removes it. The job is consumed. Kafka does not do that. The record stays. What moves is the reader's position. So, five different programs can read the same record at five different times, and it does not go anywhere. It sits there until we tell Kafka how long we want to keep it. So, if somebody asks you what Kafka is, you can already answer it. A durable shared log that lot of programs can read independently. And everything else we do from here is just how it manages that and what it costs us. So, let us start with why anybody wanted this in the first place. So 2010, LinkedIn. And the thing is, their problem was not something was slow. Their problem was the sheer number of integrations. Every system in the company needed data from every other system. Search, recommendation, analytics, the data warehouse, and each one of those was a separate pipeline that somebody had to build and then maintain forever. So let us say we have six systems producing data and six systems that want it. That is 36 separate connections. And one more consumer, and we are adding six more. It does not grow gently, it grows by multiplication. So the idea Jay Krebs and his team landed on was this: stop connecting systems to each other. Everybody writes into one shared log, and everybody reads from that same log. And now, 6 writing and 6 reading is 12 connections, not 36. And a new one is 1 connection, not 6. We have gone from multiplying to adding. And by the time they published the paper in 2011, it was handling close to a billion messages a day. But think about the kind of problem that was. Because that is what tells us when to reach for it. It was not make this faster. It was let lot of independent systems read the same data, each at its own pace. So, the log. Picture a notebook, same as that passbook, and let us take something concrete to hang all of this on. Say, we are running a small online shop and we will carry it the whole way through. So, every time an order comes in, a new line gets written at the end of that notebook and it gets the next number, line 0, line 1, line 2, like that. And that number has a name in Kafka. You will see it everywhere. It is called the offset. Offset is just the position of a record inside that notebook. That is all it is. And there are two rules here. And I think they sound restrictive at first, but they are the whole trick actually. One, we can write at the end only. We cannot insert something in the middle. And we cannot go back and edit line 2. 2. Reading does not remove anything. The notebook does not shrink because somebody read it. So, why design it like this? Think about what the mission actually has to do here. Writing at the end of a file again and again is one of the fastest things a computer can do. No searching for a spot, no shuffling things around, no updating a record in place. It just keeps going in a straight line. And the second rule is what buys us everything else. So for our shop, every order that comes in is one line in the notebook. The payment system reads it, the email system reads it, the analytics system reads it as well. Same line, three readers, and nobody is taking anything away from anybody. That is the important part. Right, the vocabulary. And at high level, five words carry almost all of it. A broker is one Kafka machine, one server. and you almost never run just one. You run a few together, and that group is called a cluster. The cluster is the thing your applications actually talk to. A topic is a named stream of records. So our shop would have a topic called orders, probably another called payments, maybe one called user signups. And for now, think about each topic as its own notebook with its own numbering. At high level, a topic is how we keep unrelated things apart. And in a couple of minutes, we will open up and see it is actually made of more than one notebook. But hold that thought. And then the two sides. A producer is any program that writes records into a topic. For us, the checkout service, every time somebody places an order, and a consumer is any program that reads them. And that's it. Broker, cluster, topic, producer, consumer. Almost every Kafka diagram you will ever see is made out of these five things. And one smaller thing which matters later. A record is what actually gets written, and it has two parts you care about: a value, which is the real data, the order details, and a key, which is optional, and which is going to turn out to matter enormously as well. And notice what you can do now. If somebody says to you, point your producer at the cluster and write to the orders topic, there are no mystery words left in that sentence. That is the whole reason we did the vocabulary first. So far, our topic is one notebook, and one notebook is written by one machine, which means at some point it is as fast as it is ever going to get. So, Kafka does something simple. It lets you cut a topic into several notebooks, and those are called partitions. A topic with three partitions is just three separate logs, each with its own numbering, that happen to share a name. And this is where the broker comes back. A partition lives on a broker. So three partitions can sit on three different brokers, three different machines, and all three are writing at once. That is how Kafka scales, not by being clever, by having more notebooks. And the offsets are per partition, which does surprise people. Partition 0 has a line 500, and partition 1 also has a line 500, and they have nothing to do with each other. So, when an order arrives, which partition does it go to? And this is where that key comes back. If the order has no key, Kafka fills up a batch for one partition, then moves to another. So, it spreads out evenly over time. And you do not control where anything lands. But if it does have a key, let us say we use the merchant ID, then by default, Kafka hashes that key and uses that result to pick a partition. And the consequence is the important bit. The same key always goes to the same partition. So every order from merchant A7 lands in partition 1, always. And that gives us the single most useful rule in Kafka. Records inside one partition are strictly in order. Records across different partitions are not. So, because every A7 order is in partition 1, we will always read A7's records in the order Kafka appended them to that partition. And that is a real guarantee, right? And we keep that guarantee as long as nobody changes the number of partitions and nobody changes what we use as the key. Hold on to that, it comes back later as the two things that are genuinely painful to change. But if merchant A7's orders goes into partition 1 and merchant B2's goes into partition 2 and both happened in the same second, Kafka will not tell you which came first. There is no single global order across the whole topic, and that is the trade you are making. You get parallelism and you give up one universal timeline. So think about the key like this: a key is telling Kafka which records have to stay in order together. So let us say our topic has three partitions and we want our payment service to keep up. So we run three copies of it. Now, how does Kafka stop all three copies doing the same work? That is what a consumer group is for. We give our consumers a group name, payment service, say, and Kafka treats them as one team and hands out the partitions between the members of the team. And the rule for a traditional consumer group is this: each partition goes to at most one consumer in the group. So, for example, three partitions and one consumer. That consumer reads all three. Add a second one, they split two and one. Add a third, it is one each. And now add a fourth one, it gets nothing. It starts up, it is perfectly healthy. It joins the group and then it just sits there because there is no fourth partition to give it. So, this is worth remembering and it catches a lot of people out. In a traditional consumer group, adding more copies of our app helps only up to the number of partitions. After that, they are idle. So, the partition count itself is our ceiling, and we pick it when we create the topic. We can add more partitions later. It is just not free. And we will get to that why. And I keep saying traditional because Kafka added a second kind of group recently. We will come to that as well. And now, the part that makes Kafka properly different from a normal queue. A different group, email service, let us say, reads the same topic completely independently. It has got its own position in every partition, so payments can be fully up to date, while email is 5 minutes behind, and neither one affects the other at all. So the group is the unit of consumption, right? And groups do not know about each other. And one more thing about groups, because this is where it becomes a problem for people. Whenever a consumer joins the group or leaves it, a deploy, a crash, our platform starting one more copy, Kafka has to hand the partitions out again. And that is called a rebalance. And while that reassignment is happening, the group is not reading, it is a pause. So, what that means in practice is churn is expensive. A group that is constantly scaling up and down spends a real part of its life handing partitions around instead of doing the work. Okay, so now let us take one order and follow it the whole way using every word we have learnt. A customer checks out. Our checkout service is the producer and it writes a record into the topic called orders. The record's key is the merchant ID A7. Kafka hashes that key and picks partition 1. The record goes to the end of the partition 1 and gets the next offset. Let us say 4102. And it is sitting on a broker now and copied to a couple of others as well, which we will come to. And on the other side, our payment service is running as a consumer group. One of its consumers owns partition 1, so it is sitting there reading forward. It reaches 4102, reads the order, and charges the card. And now it has to note down somewhere that it is finished with this one, and that is called committing. And there is a small detail here worth getting right because lot of explanations get it wrong. When a consumer commits, the number it stores is not the record it just finished. It is the next one to be read. So it finished 4102 and it commits 4103. Think about the marker as sitting in the gap between two records and pointing forward, not sitting on top of the last thing we did. And Kafka stores that number for us on the cluster for that group. And why does that matter? Because if that consumer dies, another one picks up partition 1, asks Kafka, where was my group up to? Gets 4103 and carries on from exactly there. And at the same time, or 5 minutes later, or tomorrow, the email service group reads that same 4102 of the same partition. It has got its own position. Nobody took anything away from anybody. And think about who is actually in charge here, because this is the part people miss. Kafka does not push records at our consumer. The consumer asks, it says, give me from 4103, and Kafka hands them over. So that position belongs to us, not to Kafka, which means we can move it backwards as well. Set it to 3000, and we read all 1000 of those records again, exactly as they were in the same order. And that is what people mean when they say replay. A service was down for a day, or we shipped a bug and processed a week of orders wrongly, or a brand new service needs last month's history. We just point it at an older position and let it run. And one condition on that, which we will come back to properly. This works only as long as those records are still there. Kafka does not keep everything forever, and we are the ones who decide how far back it goes. And that is the whole mission, really. Producer, key, partition, offset, broker, group, commit. Everything after this is a detail on top of that. So, machines die. What stops us losing orders? Replication. Every partition is copied onto more than one machine. So, the same data is sitting on two or three brokers, not one. And one of those copies is in charge. We call it the leader, and that is the one doing the reading and the writing. The others just quietly keep up with it. So, when the leader machine dies, one of the copies that was keeping up takes over, and we carry on. That is the whole idea. The data was never in only one place. And there is one choice here that is worth knowing about. When our producer writes an order, it can carry on as soon as the leader has it, which is fast, or it can wait until the other copies have it as well, which is safer and a little slower. So, at high level, that is a dial between fast and safe. And we are the ones who pick where it sits. And honestly, for what we are doing here, that is enough. There is a whole set of settings underneath this, exactly how many copies you have to confirm and what Kafka should do when some of them fall behind. And that is a proper operations topic on its own. So I'm not going to pretend it fits into this video. So, if reading does not delete anything, does Kafka just keep everything forever? No. We tell it what to keep. And there are two completely different ways of answering that, which people mix up all the time. The first one is retention, and this is the normal one. We say keep 7 days, which is the default as it happens, or keep 500 gigabytes, and anything older than that gets thrown away. And it gets thrown away in blocks. Kafka stores a partition as a series of files, and it drops whole files of the old end. So, if it is not tidying up individual records, it is dropping the oldest chunk. And the question retention really answers is how far back can anybody replay? So, if a service is down for 2 days and our retention is 7 days, it can catch up completely. If our retention was 1 day only, that data is gone. The second one is compaction, and it answers a completely different question. With compaction on, Kafka keeps at least the most recent record for each key and eventually cleans up the older ones. So, a topic keyed by user ID becomes roughly the latest state of every user, and that word eventually is doing a lot of work there. The cleaning runs in the background on its own schedule. So at any given moment, we may still see older copies sitting around. So it is not a table we can query for the current value. It is a log that gets tidier over time. That is the whole thing. And let us say we want to actually delete a key from a compacted topic. Then we write a record with that key and no value at all, a null value, not an empty one. And that is called a tombstone. It means the key is gone. And honestly, this is the part where people realize Kafka is not a general purpose query database. Think about it. Deleting one user's data is not a delete statement here. It is writing a marker and then waiting for a background process to get it. So, at high level, retention answers how far back can we go, and compaction is how we keep at least the latest value for each key without keeping every version forever. Two different questions. And I think most topics we will ever build just want retention only. And the number we pick, there is a direct storage bill, right? So it is a real decision, not a default to leave alone. So, four things that actually go wrong. And the first one is the most common by a distance: consumer lag. Our consumer is reading slower than the producers are writing. So, the gap between its position and the end of the log keeps growing. And the thing is, nothing looks broken. Every broker is green. The consumer is running. It is just behind an hour, 3 hours. And the Kafka cluster does not read that as a failure. And as far as Kafka is concerned, nothing is wrong. So it is on our own team to watch it. And the useful thing is to look at that gap per partition, not as the one number for the whole topic. So if every row is falling behind, the first thing to check is whether our own processing is slow. Some call we are making, some query. Fix that first. Then add consumers if there are partitions free for them to take. And only add partition when the partition count itself is genuinely the limit. But if one row is enormous and the rest are fine, that is a different problem. It is not overall speed. It is that one partition, uneven traffic, or one expensive record, or something downstream that only that partition touches. And the most common reason is the next thing on the list. Second, duplicates and losses around a crash. So remember, the consumer does the work and then commits. What if it dies in between? Another consumer picks up, sees the old position, and does that record again. And our customer gets charged twice. Now, let us say we flip it around and commit first to avoid that. Then, a crash means the record is already behind the marker and nobody ever comes back for it. It silently just never happens. So, when the commit and the work are two separate operations, we are choosing which risk we want. And almost everybody chooses the repeat. That pattern is called at least once and then makes the work safe to do twice. We key the charge on the order ID, so running it again does not charge again. Third, a hotkey. We said the same key always goes to the same partition, right? So if one merchant is 40% of our traffic, then 40% of our records are in one partition, being read by one consumer. while the others sit almost idle. And we cannot fix that by adding machines. The fix is a different key, something finer than the merchant, or deliberately splitting that one merchant across a few partitions and giving up strict ordering for them. And fourth, the one to be careful about, adding partitions later. So, with the default partitioning, Kafka hashes the key into a number and then takes the remainder when we divide that number by partitions. So, which partition we land on depends on how many partitions there are. Now, change that number and the same key lands somewhere else. Merchant A7 used to go to partition 1, now it goes to partition 3. All their new records go to the new place. All their old records stay where they were. And Kafka does not automatically give us one ordered history for that merchant across both. And we can add partitions, but we cannot remove them. So, the partition count and what we choose as our key are the two decisions here that are properly painful to change later. Think about those two harder than the rest. And two things have changed recently. Enough that most of what we read online is out of date. So I want you to not get confused by them. The first one, if you look up a Kafka diagram, there is a very good chance it has a box on it called ZooKeeper, a separate system that Kafka used to need just to keep track of itself. That is gone. Kafka 4.0 in 2025 removed it completely. Kafka manages its own metadata now, and that mode is called kraft. So we do not need to learn ZooKeeper. And if a tutorial is telling us to install it, that tutorial is old. And the second thing, and this one changes something we said earlier. Remember the rule in a traditional consumer group, a partition goes to one consumer, so a fourth consumer on three partitions just sits there. Newer Kafka added a second kind of group where consumers can share a partition between them, so that fourth one can finally do some work. And the trade is exactly what you would expect. Once several consumer are pulling from the same partition, the records can come out of order. And ordering inside a partition was the whole reason partitions exist. So, it is a useful option when what we actually wanted was a work queue. Underneath, it is still a log. So, when is Kafka the right answer? Three situations really. When several independent systems all need the same data and none of them should be able to block the others. When you need to be able to go back, replay history because a service was down for a day or because a new service needs the last month of events, and when the volume is properly large. And when is it the wrong answer? Honestly, more often than people admit. If what you want is this service should reliably tell that service something happened, then that is a job queue, and Kafka is a lot of machinery for it. And think about what you are taking on properly. Partitions you have to size and cannot easily unsize. Consumer groups and rebalancing, offsets and commit semantics, lag monitoring that nobody builds until the first incident, retention policies and the storage bill, and brokers to run and upgrade as well. And let us be honest about our own shop, right? If you are doing 2000 orders a day, that is under 2 a minute, then every single thing we have been through is missionary. We took on for no reason. And there are real teams out there running Kafka for 50 messages a hour. I think most teams never outgrow Kafka technically. They just reach a point where the cost of running it stops being worth what they get out of it. So, for the simple version of the job, RabbitMQ or SQS if we are already on AWS or Redis streams, or honestly at small scale, just a jobs table in the database we already have. And we can put Postgres, listen, notify on top of that to wake the workers up quickly. But the table stays the source of truth because a notification can be missed if nobody is listening. All of those will reliably tell one service that something happened, and none of them will ask us to think about partition counts. So let us put it all back together at high level. Kafka is a log, an ordered list of records where we add at the end only. And reading removes nothing. A named log is a topic. A topic is cut into partitions, so several machines can write at once. And the record's position inside its partition is its offset. Programs that write are producers, programs that read are consumers, and consumers working together as a team are a consumer group. And a partition is copied onto several brokers, so losing a machine does not lose our data. And if you keep only three things out of all that, keep this. The partition is the unit of both ordering and parallelism. Order is guaranteed inside a partition and nowhere else. And in a traditional group, we cannot usefully have more consumers than partitions. The key decides which records stay together. which is exactly why the key and the partition count are the two things that are hard to change later. The record and the reader's position are two separate things, and that is why several teams can read the same data independently, why we can replay history, and why a consumer can quietly fall hours behind while everything looks perfectly healthy. And that is Kafka properly. It is not a faster queue and it is not a database we can query later. It is a shared, durable log that lot of systems can read at their own speed, which is genuinely powerful when that is the thing we need, and a quite a lot of machinery when it's not. See you in the next one.